Okay, welcome back to Data Structures. Today we have Chapter 6. Chapter 6 is on lists. In Chapter 1, we went over linked lists a little bit in concept and lists. This lecture is not entirely just a repeat. It adds some more examples and applies it, and the focus is on different types of lists, not just linked lists. So the list concept is the focus of Chapter 6 and today's lecture. So we're going to examine the list processing and the various ordering techniques of lists in terms of its data structure purpose, and defining a list abstract data type, and introduction to the concept of an iterator, which we've actually kind of seen already. We saw iterators, I believe, with array lists and some queues and stacks and things in terms of the built-in Java data manipulation packages. We'll examine polymorphic features of the VIA interfaces that are used with lists as well, and demonstrate how lists can be used to solve problems, and examine various list implementations, and then compare the implementations across the board. So this is actually kind of an easy lecture compared to what the stacks and the queues and stuff like that is about. So lists are linear collections, so it's part of the collection class. We have different types of lists like stacks and queues, but they're more flexible. So the list, I would almost say, is more generic than a stack and a queue. It's a little bit more flexible as well. You can add different functionality to it, extend the concept, so it's not really a stack or a queue, it's a list. Adding and removing elements in the list are not restricted by the collections structure themselves, so it's not following a queue where we're adding to one end and taking away from the other. Not following a stack where it's added and removed from the same end. So as we don't have to operate on one or both ends or either ends. So lists are really defined by the ability to add and remove from anywhere in the middle of the list, or anywhere and any point in the list. So we're examining three types of lists of collections. We've got ordered lists, unordered lists, and index lists, which are the three combinations that we'll look at in terms of the collections class. The elements of an ordered list, as you might imagine, are ordered by some inherent characteristic of the element, usually by the name, maybe name in alphabetical order, or maybe a numeric order, scores of orders. It doesn't have to be. We can actually come up with an ID value or something and order the list by its data element and create like a fake ordering system for it, like an ID. Therefore, the elements in the list themselves determine where they are stored in the list, and the elements are keeping track of themselves, putting themselves in their own order. And here's a conceptual view of the ordered list, where we have from the list we have a bunch of numbers, and they're in sequential orders. So if we wanted to add the number 54 to the list, it would go between 49 and 57, according to this kind of structure. We do have a front, we do have a tail, and we add an element anywhere in the list, which makes it the implementation of this type of list has to have a little bit more functionality than a stack or a queue. And it doesn't necessarily need to be implemented like a linked list. It could be an array list, it could be any type of list. So the lecture actually comes through with a bunch of different examples of different implementations, which you want to get out of this. So the ordered list we looked at has the order in particular sequence, and this is numeric. Unordered lists, there's an order to the elements in an unordered list, but the order is not based on the element characteristics. Instead, it's on the insertion, or it's on some other thing. So the user of the list determines the order of the elements. So it could be like a first come, first serve, first in is the first item in the list, second item in the list. It could be a random order, or it could be no apparent order, but there is an order. So there's always an order because you have to keep track of all these items. But is the order important? If it is important, then you use an ordered list. If it's not important, then you use an unordered list. And it allows you to take advantages of some of the search efficiency. If it's unordered, usually has to be ordered before you can search it. But insertion and deletion are usually a little bit quicker. If it's an ordered list, it's easy to search. Really quick, but insertion and deletion take more time because you got to shift items. And it's more time consuming in terms of the algorithm for searching, sorting, and inserting. So a new element can be put at the front of or the rear of the list or in the middle of the list. It can also be inserted in any particular element already in the list. So it can be put anywhere you want. Here's adding an item to the list, conceptual view, adding it in the middle, adding it to the end. It doesn't really matter. If it's an unordered list, it doesn't really matter where it comes in. So you don't really have to keep track of which location you're going to put that into. And then we have the index list. So the index list, elements are referred to as in a numeric position in the list. Array lists are generally considered index lists because the array index has a 0, 1, 2, 3, 4 for the size of the, let's say there was 5 items in the array, it would be 0 through 4. And so we have the index value if we're using an array index in terms of the array elements. However, we don't have to use an array for it. We can still have an index list without an array implementation. We can have an ordering system that is external to the list itself in terms of the contents of the data items that are being stored. And we could have element 1, element 2, element 3, element 4, just arbitrary numbers that we've assigned to these nodes or elements. And we could put items in the elements. So like in an ordered list, there's no inherent relationship among the elements, and the user can determine the order. Every time the list changes, the indexes are updated. Here's an example of an index list, and here is the index. So you might consider an index list the same as an ordered list, except the index is external, and that the list items themselves are not determining the order. So adding an item to the list, you could start it to 0, you could remove it from 7, you could put it in the middle. Doesn't really matter what you do with it. But indexed lists are more than just array lists. So, list operations. Several different operations that are common among all of these different list types. These include removing elements in various different positions and checking the status of different elements in the list. The key differences between the list types involve the way the elements are actually added. Here's some common operations on the list structure. Remove the first, remove the last, remove any particular item in any order. It doesn't have to be the first or last. Give me the first, get me the last. Determining if the list actually contains a particular item. Emptying, is it empty? What is the size of the list? How many are in there? So usually with a list versus a stack or a queue, a stack or a queue, well, the stack's going to have the pop and the push, the queue's going to have an in queue and a D queue, and they're going to be predetermined by the way you design the data structure. Predetermined to meet the style of the addition and the removal. The difference with a list is that it's usually determining where first, and then the insert or the deletion is dependent upon the position. And the technique might change depending upon where you're at. If you're at the beginning of the list, the end of the list, the middle of the list. And there's an ordering consideration. As an example, if it's an ordered indexed list, you have to update two things. You have to update the list and you have to update the index. If it's an ordered list, you have to reorder the list. If it's an unordered list, you know, there's other things you may have to take into consideration. So it's the implementation details that vary. The structure itself is really the same. You can implement it using pointers, you can implement it using arrays, you can implement it using any data structure technique that you want in terms of the creation, but the elements themselves are differentiated by the way they're accessed and used. So the operation particular to an ordered list, the add, adds an item to the list. So the order is basically going to be at the end of the list normally. If you're going to add an item to the list, you also could add it at the beginning of the list. There's no requirement that says it has to be at the end. Operations that are particular for an unordered list might be add to the front, add to the end, add after something. So you could, for example, have an alphabetical list, and maybe it's by first name, and a new name comes in. You can find where it's supposed to go, and then add after that, and then add after that. So your insert doesn't actually add at the beginning or at the end. Instead, it adds wherever it's supposed to be, you know. And you can actually implement like a linked list if you wanted to for that, to insert where it's supposed to go, theoretically. So you might imagine actually that the operations that you're performing are a little bit more complex for a list, because it's not quite as easy in terms of each new item that gets added in a slightly different spot in the list. So in a queue or a stack, it's kind of easy to implement that because it always gets added to the same spot. Every add is identical. In a list environment, the add is not predictable. where we're going to add this item, which is where the technique comes in. We also have some other list operations. As with the other collections, we use the Java interface to determine the collection operations. The collection operations, if you recall the interface, can be defined via inheritance, derived from other interfaces. Actually, if you're here for the Java class earlier today, talked about interfaces today, which is kind of ironic. But it uses an interface to implement behavior for the methods that are needed for the insertion, for the deletion, for all the behavior. So we can define a common list operation in one of the interfaces and derive 3 others from it by defining interfaces of the 3 list types. So we can have an interface that is inherited by another interface. So we can have a basic insert function as an example. It's in an interface, and we can build another interface from it that inserts at a particular location if it's this type of list, and then it inserts a different way if it's that type of list, for the 3 types of lists that we have. Here's some various list interfaces. The interface list add, abstract data type for the list itself, where we have remove first, remove the last, remove an object. Here, I'll make this a little bigger so you can actually see it. Get the first, get the last. Is it empty? The size. These are the methods that we saw in the previous example. Kind of generic. Usually there's a toString added in there. The toString does nothing more than print the list item in the string, so it can actually view, see what's in the item. In terms of these 2 interfaces that might be inherited from this list kind of interface, we might have an ordered list or we might have an unordered list interface. And the ordered list is going to add the comparable. The comparable object is one in which we're going to implement maybe an interface for comparable that's going to take and do a compare this object to this object. Is it greater than or less than? It's greater than, okay. Is it this object to this object? Oh, it's greater than, to find a location for which it should be numerically ordered in the list. Or perhaps a string, is it less than or greater than the particular value of another string or character that might be in the list. Unordered, add to the front, add to the rear. Add after an object, any arbitrary object, target object. I don't know why people would do that actually. Maybe pick the middle of the list and add after, and everything is added in the middle of the list maybe. Interesting. I would just basically add to the front or add to the end if I were going to arbitrarily add items to a list. I usually put it at the end of the list maybe if I'm going to make a list. You don't actually have to put it at the end of the list, though. You can put it anywhere you want in the list if there's no order to it. So. You could be thinking ahead of time, though, and going, well, let's do a binary kind of logic. If it's less than 50, we have 100 items in the list, and say, it's less than, the item number is less than 50, put it over here. Higher than 50, put it over here, or something. Okay, so here's the interface. This is what the Java code would look like for the interface, and this would be for the interface for the list item at the top of the box, or this guy right here. What I'm going to show you are the 3 different interfaces. The first one here is just nothing more than a definition of the general list collection. So what we're looking at then is the list that extends iterable. It's making it's adding an iterator, essentially inherited from iterator, that's going to essentially give us the ability to go through the items. So it removes and returns the first element of the list. Remove method for removing the first, and then here's a method here to remove the last. And these are just like the function, the method prototypes, the signatures, essentially the header of the functions that we're going to be implemented in the classes that use it. So this would be the interface to the class. Get the first, get the last, return the last. Look at does it contain this item? If this item is in there, put it next to this other item or something. So you can organize the list. I could see, grouping similar items together, perhaps in the list. Maybe you have a list of books, and you want to put all the books by one author together. And so you find the author, add it to the end of that, the last author that was in there from this book, list of books or something. Is it empty? The one on the bottom there returns the size, perhaps. Use the iterator, returns the iterator elements of the list to get the elements out of the list, and then convert them maybe to a string so you can print them. You can print them out. So And this is the one for the ordered list interface, for which is going to add the add element to add it to element to the particular list as the last item. An unordered list, and in the unordered list we're going to have an add to the front, add to the rear, which is going to be this one, or add after a particular element. So what we're going to change in the interfaces are pretty much the add functionality. The other functionality of the list is pretty basic. And it's going to be all the same. So the differences between these three different types of lists is going to be how we're adding items to it and how we're going to take away an item. What happens when we take away an item. So when the add is more complicated than the taking away, actually, think about it. When we remove an item, all we have to do is remove it and then fix the hole. If there's a hole, if there's no hole, we don't have to worry about it. We just leave it alone. When we add an item, we have to figure out where are we going to add it. So I guess you could probably figure out, well, which item are you going to remove? So you can do a comparable with one object to another. So let's go through a little example and kind of put this into practice. We're going to come up with a list for a tournament maker. So we're going to use an ordered list to help manage bowling tournaments. So we have a bunch of bowlers that we're going to put into teams, and now we're going to manage the different lists of teams. So we have teams that are ordered by their number of wins in the regular season, and we're going to create our first round matchups where the team with the best record is matched against the team with the worst record. Of course, the team with the best record is probably going to win. And the second round is going to be matched against the second worst team, the third worst team, until we get to play themselves eventually, probably, whoever's left, depending upon who loses. Here's the bowling league team and the number of wins. So we've got scorecards, gutter balls, kingpins, pin doctors. These are bowling league team names and the number of wins. So the scorecards have the highest. Wood splitters have the bottom ones. So these two guys will be playing first in our list. So we keep track of the list of the players on the team. We can actually keep track of the teams in this particular case, along with their number of wins. And a sample tournament layout for the bowling league tournament might look like this. We have game number 1, the scorecards versus the win splitters. That's the 10 and the 2 team. So they got matched up. And then gutter balls and the 10 pins and the king pins and the splits, and you can follow through the rest of it. So basically it's the layout for how you're going to match the teams up. And it looks like we got 7 games going on here in terms of our tournament. So if we're going to make a Java program to implement this using data structures that we've learned about lists, how would we implement it? Well, here's a good way. So the class that represents the team will be a comparable based on their number of wins. So we're going to implement a comparable interface that's going to be able to compare the objects based upon the data element that's keeping track of the number of wins that each particular team has received. So the tournament will be the driver for the program, and it will demonstrate the first round of the tournament team matchup using the ordered list. So here's our driver, tournament, and in our main we're going to say tournament maker temp is going to make a new object, a new instance of the object of tournament maker, which is the program that we're going to run here, and we're going to say temp.make, and the make method is going to make our matchups and make our tournament work, essentially. And so we have our team, and team represents the team. So we have a team object that's going to we're going to have 7 of these objects, 1 for each one of the teams, and the team is going to implement comparable, because we need to implement the functionality that's going to be able to take essentially each one of the teams and be able to compare it against another team. So the objects will have something in common in terms of a comparison, which is going to be essentially the variable that we're going to keep track of in terms of the wins. So we set it up, kind of a generic team. The team's going to have team names, the name, and the wins. So we have, it's kind of a simple, we're not carrying that much data. We could essentially add more stuff for each one of the team, but the name and the number of wins is what we're interested in. So we're going to have a function that says get name. We're going to have a set name. We're going to have a get wins and set wins, obviously. We're going to have one that does comparing. So we're going to compare the number of wins of this team to another team. So it's going to return -1, 0, or 1, depending upon whether or not it's less than, greater than, or equal to. Not necessarily in that order. Actually, it's less than, equal to, or greater than the other team that we're comparing it to. And when we do that, we're going to use a compare to method that's going to return this wins versus the other wins. So it takes this object and compare it to the other object that we're comparing it to and say, well, we have 2, and the other object has 10, so we're lost. That we're smaller than the other object. And then return the name of the team. Because what you can do is kind of iterate through all of the different objects. Find the team with the highest score, find the team with the lowest score, and basically assign them and say, okay, you guys are going to play a tournament. And then go through the next highest with the next lowest. And then you can have your first round where all the teams are matched up by their lowest and highest levels. And then the second round and third round, as the problem description kind of alluded to in terms of the matching of the teams. And then toString to print out the name of the team who's got the score, who's been matched up with the other team. So here's our tournament maker class that demonstrates the first round of the tournament team matchups using an ordered list. So the key here is that we're keeping track of the order with the essential scores that have been accumulated here. So what we're going to have is a basic, in fact, this is runnable code. You can cut and paste it, put it in, and you can actually see how this works in terms of the implementation. Determine and print out the team's organization, essentially. I'm going to throw an IO exception, if we get one here. And we're going to implement it using an array ordered list, and we're going to have an array ordered list of team objects. So we're going to cast it a team data type that's going to be stored in here. Just realized you guys probably can't see this. And it equals a new array ordered list. This is pretty. We saw this a couple weeks ago in terms of the examples that we were looking at. Same kind of format, but the array ordered list is going to be part of the collections that we're including in utils. String team 1, string 2, team name, number of wins. Keep track of the wins, keep track of the team names, and then check the input. And then this is the scanner class. It actually takes in information. You can scan information as a stream. I'm just going to take it in from the system input. And then it allows you to enter in from a keyboard, capture the input, copy it into an input stream, and then use the input stream to print something out or to use the data inside of the program. While the number of teams divided by 2 is not equal to 0, teams is equal to 0. Team input is not 0, meaning while we're getting input from the keyboard. Enter the number of teams. It must be an even number of teams, because you have to be able to do an even matchup. If you have an odd number, you're going to have one team that can't play anybody. It has to sit out. So you have to put in an even number. I don't know if you can have 7, I think, in there. I might only be able to put 6 of them in there then, or 8. And then it checks to see if the team is valid for the single elimination round, because you can't have a team to play itself. Basically, one team needs to play another team. And then we can go through and set the system output to, enter the next team, enter in the next team. And then eventually we're going to have to go through a loop here, count it up, enter in the name, enter in the wins, enter in the name, enter in the win. Essentially populate the program with a bunch of data, with a bunch of teams and a bunch of scores that are associated with the teams. And then create the tournament. So team 1, tournament, remove the first one. Team 2, remove the last one, because we're going to sort this in the order for which the numbers. So in an ordered list, we're going to sort it by the number of wins. So it's going to go 10, 9, 8, all the way down to, I think the last one only had 2. So it's going to take the first element and the last element, and then the first element and the last element, and the first one and the last one until it runs out of matches. That's one of the advantage you have of using an ordered list. Once you create the order of the list, you don't have to determine any of the positions anymore. It's kind of like how we do a binary search on an ordered list. You'd order the list first. If you're going to do a binary search, you'd order the list. And you guys are familiar with binary searches? Yes? We all know what a binary search is? Nobody's responding. If I had a list of 100 items, and they were in alphabetical order, actually, let's say they're numeric order, and I have 100 items, and they're all mixed up. I have 100 teams. I have 100 of these bowling teams. they have scores between 0 and 100. And I put the scores in an order. The most efficient way of searching for a number to see what position is that in, what team is that, find the number, is to take the entire list and order it first, and then look at the center, cut the list in half. So 50 would be the half between 1 and 100. And I go, well, is the score higher or lower than 50? And if the score is higher than 50, if it's like 60 or something, if the number I'm looking for is 60 to see what team got 60 or something, then I can get rid of 1 through 50. Why do I need to search through that? So it cuts the search space in half, which is why it's called a binary search. Take it, and binary is 2. Make 2 out of it. Is it higher or lower? It's lower. Get rid of the higher part. So then you take the lower part and you cut it in half. So is the number I'm looking for higher than, what's between, let's say, 50 and 100? What's the 70? I don't know. Like 75. Is it higher than 75 or lower than 75? It's higher than 75. So I can get rid of 50 through 75. Now I got 75 through 100. And I can go, well, maybe the number's 80. And I can cut that in half. Eventually I'm going to get to the number faster than if I go 1, 2, 3, 4, 5. Because the problem with searching algorithms is the search space. The bigger the search space, the longer it is to find what you're looking for. Isn't that always the case in real life? So if you can wipe out half the population right there, then in terms of a binary search, it's the most efficient way of searching, because you're constantly, with each attempt to find the item, you're searching half the search space, and then again half of that, half of that, half of that, to get to the point where you got very small. You got 5 numbers you're working with. It's got to be one of the 5. And it's easier to find it, and then you can figure out, oh no, it's not in here, or it's in here. So you can come up with a solution a lot easier if you're getting rid of your search space anyway. Long story short, this is not using that, but instead it's using an ordered list for which it doesn't really have to care, just like a binary search. The reason why I brought up the example, it doesn't really care what's in the list. It just picks the top and the bottom, takes it off. Picks the top and the bottom, takes it off, because we want to match up the highest score with the lowest score. So it's kind of a similar kind of logic in which we're not going to use the list. We don't have to search through the list anymore. We can just treat the list as a bunch of numbers. And kind of like an unordered, but we're just interested in 1 or 2 particular locations on it. Here's how the big picture, this is our application. So these are classes that we will be using in this program for the bowling team competition. It's like, what was the theme of this? So we have the team with the 2 data members, and the 2 data members would be the team name and the wins. And then we have the team, the compare to, and then a toString, so we can print out the information from the object. And the compare to is going to compare it to another team. Compared to another team, are your wins higher or lower? Compared to this other team, are your wins higher or lower? So it works with the array ordered list. So the team is actually the object that is inside of the ordered list. And because this says array ordered list, we didn't actually create an array. We're using the collections array ordered list, which is actually an indexed ordered list, because the array gives index values to it. But we're not using the index features of it. We're just treating it like a generic list. We have the team maker that's going to make the teams from the positions in the list. So we have the make function that takes the high and the low, high and the low, high and the low. Then we get the next token, essentially is going to get the next item. So we already pulled off the high, so next take the next one. And then the tournament, which is nothing more than the main program, and the main program is using the tournament maker that uses the team to select the highs and lows from the list to put it together. And the list here is extending from these 3 interfaces: the ordered list abstract data type, the array list, and then the list abstract data type, which is where that interface is coming from. This is all given to you in Java API, and these are the 3 kind of classes we're looking at. And this ordered list is the foundation for keeping track of the order of all the teams. So not a bad implementation. In fact, that's one of the interesting things about data structures in general, is you can apply the same concept over and over again to like different applications, and it all works the same way. So you learn how to do the data structures, and then when you find an application that needs to hold something, then you go, well, there's a data structure for that, and use the same one you used, last time you created a similar type situation. The talent is figuring out which data structure to apply for which solution to make an efficient solution out of it. Because we all know we can do anything we want. We could not even use an ordered list for that. We probably could use an unordered one, but the problem is the application going to run as fast as if we use the right data structure? So the point of studying data structures is to make a program that's efficient, that runs, not only does it not make a lot of data, unnecessary data that has to be translated and stuff, but proper data storage and proper data manipulation with speed, because nobody wants a program that runs slow. So let's see if I can pronounce this right. We have the Joseph problem. Josephus. And it's a set of elements that are arranged in a circle. So we got elements that are arranged in a circle, starting with a particular element. Every jth element, nth element is removed. So 1, 2, 3, 4, 5, take one off. 1, 2, 3, 4, 5, take one off. Processing continues until there's only one element left. The question is, given the starting point and remove the count, which element is left? It's kind of like that game. Well, it's kind of like spin the bottle. You spin it, it hits somebody, okay, you're out. Spin it, you hit somebody, you're out. So how many times does it go around, or spin the wheel? It goes around and you hit a spot on the circle, and so that is removed. So you have fewer items to spin to next time. So is it a fixed count? Is it a variable count? Does it always go 5? Does it go 5, 6? Incrementing the counts. And then which item is going to be left? Is the winner, right? So when you spin the bottle, it's the person that is left. That hasn't been eliminated out of the circle. You guys are familiar with that game, right? No, maybe not. In the U.S., the spin a bottle game? You guys are laughing, so I guess you are familiar with it. You have to take an item of clothes off if the bottle hits you. And if you have no more items of clothes left to take off, you leave the circle. So, it's a game. Come on. Alright, perhaps not appropriate for all settings, but it is a game. And it does lend itself to this example. So it's a Joseph's class circle that we can say, now we know what that means. Alright, so we're going to use an array list, and we're also going to look at the scanner class again to take the input in. So we've got our class here, Josephus, if I can say that right. Anyway, continue around the circle, eliminating every nth soldier. Now we're going to have soldiers here instead of people, until all of the soldiers have been eliminated. I guess you can call this a firing squad. But most of the firing squad games that you see, the violent video games you see, is usually a soldier shooting at civilians and they're all lined up against a wall. We can turn this in all different directions. So, the concept's still the same, except for the wall is not a circle. And that's not fair. So, what do they call that? Russian roulette? The original game of Russian roulette? You guys familiar with that? That's not a good one. That's not as fun as spin the bottle. Russian roulette, you're lining everybody up in a circle and there's a soldier with a gun. And he spins around and he stops and he shoots somebody. Or no, that's not Russian roulette. That's another game. There's Russian roulette where the two people stand next to each other and they both fire at the same time. And one of them dies before the other one, obviously. Or do they both die at the same time? Let's go back to spin a bottle. See that? Now that game seems a little bit more innocent, doesn't it? Seems a little bit more pleasant compared to these other games. But it's the randomness of the shot that I guess is enticing or interesting in terms of the circle. So there's a lot of games in the U.S. actually, like the wheel games, like Monopoly stuff. Well, Monopoly is different. It's dice. But isn't it sort of like going through a series of numbers, 1 through 6, 1 through 6? So it's the randomness of the throw, the dice, that's going to eliminate something or have some action that's performing. These are all games and examples of things you can implement in Java using the same programming technique that I'm showing you for this particular game. So we have main. Obviously, we always have main. The number of people, the gap between the people, new gap, and a counter. Because we're going to have a gap. You know, if we get rid of somebody in the circle. So let's say this is a, you know, you blindfold somebody and you spin them around and he points, or he or she points. Let's turn this into a kid's game. Points at somebody. That person has to leave the circle. And then it's the person who's left in the circle who wins. So we're going to have a gap when that person leaves, so we have to bridge the gap somehow because we don't want to hit the gap again. Which makes this game kind of interesting because when the gap occurs, it's like you removed an item from the list. And we're treating this like a circular list. And when we remove the item, we have to reorder the list to put everybody together to remove the gap. Unless we leave the gap. If we leave the gap, how many times is that person going to spin around and hit the gap? It's not very efficient. It might make sense in some cases to leave the gap, depending on how many items you're removing. But if you're getting down to one, eventually you're going to get to the point where it's spin, nope, empty, spin, empty, spin, empty. And some games are actually designed like that. And then you roll the dice, oh, roll it again, roll it again, roll it again. You get to roll like 10 times before you can actually hit a number that's usable. But in this game, we want to make it so every round is usable. So we have an array list of integers that we're going to put into the array list. This is the same thing we've seen before. Scanner, same thing, taking input from the keyboard. We're going to get the initial number of soldiers. So we're going to say, you know, we've got 10 soldiers. Enter the number of soldiers, and we take it in, each one of them using the in, next integer, in terms of a little loop here. Get the gap between the soldiers. Enter the gap between the soldiers. Can make it 0. Can make it 1, 2. Load initial list of soldiers. Load the objects in. These could be soldier objects, you know, that are holding information about the soldier. So the number in 1 to the number of people that we've decided, increment it. So list add. So this is basically adding a new integer count, and it's adding new integers to the list. So populating the list with soldiers, and the soldiers are integers essentially. So the counter is the gap minus 1. The new gap is the gap. The order is, and we're going to print out the order after each game. So we're treating lists as a circular list, and removing every nth element of the list until the list is empty. So here we're going to pick a number, and we're going to remove every nth element, reorganize the list until the list is empty, and we're going to find out who's left. So this is a nice little gambling game. But it's predictable. If the nth number is preset, it is predictable. So I wouldn't gamble on this game unless you write this program, figure out, well, if there's 10 items, then this item's always going to be left. If the counter's 2, you know, so you know which item to bet on. So here we have a remove the counter. Number of people is the number of people minus 1. Decrement it every time you remove it, the count goes down. And then eventually you're going to end up with nobody in there. So if we were to take a look at the program itself, in terms of a UML description, we would have the array list, and we have the main class here, the main driver program, and the array list, it just says this in it, and essentially we're just using the list feature of the abstract collection coming from object of the abstract list. We don't really need a sophisticated concept for this. It's just in the list, and it's just counter, and it's just removing items at particular levels. And in this example, we did not reorganize the list. We just left it so that there are some spins for which nothing can be removed. And it goes back and it has to spin until it eventually gets to it, or goes through a count until it eventually gets to the particular elements. Actually, I don't even know what we set the counter to, so it could have done 1, 2, 3, 4, and just removed them all in order, for all I know. So, in terms of implementing the list with arrays, the array implementation of the list could follow strategies similar to those that we've used for a queue. We could fix one of the ends of the list at index 0, and then shift as needed when an element is added or removed. Or we could use a circular array to avoid the shift at one end. Actually, we saw the circular array last time. However, there's no avoiding a shift when an element in the middle is added or removed. Let's examine a fixed version of this particular structure. So here's an array of elements in the list. Interesting thing about an array is that, going back to the concept of the indexes, we all know it's not the most efficient data structure to use, because we do have to shift elements, otherwise we have holes in the arrays and it throws our numbering off. So if we took out element number 2, we would have a hole here. We have to actually take element number 3 and move it into element number 2's space. Otherwise we can't just, well, I guess we could add into an empty spot in the list if we wanted to. But if we wanted to keep an ordered list, we'd have to shift the items, and that's the problem with an array and why people don't like to use arrays for implementations of lists. So an array implementation of the list, the rear would be item number 4 here, at the end of the list. So here's the list to remove operation. So the remove is expensive in terms of the efficiency of the operation. So remove an element at a specified element, specified location. We have the public T remove. T is the element, or T is the data type that we're going to use. T is the result. And so, without going through the board and all the loops and things that we'd have to actually perform, which you end up with doing a lot of looping. You know, for this is the array. For the 0 to the end of the array, I take each one of the items and shift it over by 1. Or move it over to the left by 1 to get rid of the spaces. Because if you pick the middle of the array and you removed like item number 5 and there's 10 items, you're going to got to take 6, 7, 8, 9, 10, move it over. You have to adjust it, shift it over 1 space. So, which leads to a lot of shifting, a lot of for loops. So usually with array list implementations, you see a bunch of for loops in here. So it has to find the other option, the other index, the advantage you have to an index is if you have the index number, it's easier to find. There's no searching for the index number. But finding it is not the problem. It's removing or inserting, which ends up being the expensive time factor. So let's see, this code sample here is going to go through the find, and if it contains the operation, then add the add operation to add an item to the list, and then you know, basically going through, and you'll see in each one of these you see a for loop. So yeah, you've got to loop through all the other items in the list, find the one you want, remove the item, go all through all the items in the list, move it over by 1, go through all the items in the list, find where you want to insert it, insert the item, go through. Well, before you insert it, you got to move everybody over to make a space, and then insert it. So it becomes a time-consuming type of implementation. So you can implement a list with links, and this is getting to the basically comparison with the linked list. So as with stacks and queues, you can implement a list collection with an underlining linked list. So this is why linked lists are the preferred method. Operations can be accomplished using techniques similar to those we've already looked at. However, examining the remove operation with the traditional approach, then alter the underlying representation for a comparison, we end up with an interesting shift in what we're doing. We're no longer doing loops anymore. No for this item is this item, go through all the in terms of going through all of the arrays. Instead, we're doing compare. We're using a compare to function and taking objects and comparing them back and forth. And we can go through the list, we can still go through. If the target element equals the current element, then we found it in terms of a comparison. So we're still going through each one of the items. To find an item, we actually have to go through each one of the items to find a particular element that we're interested in removing. But to add, we just find the location where we want to find, or where we're going to add it to. There's less shifting, but the same search is actually necessary in terms of finding the element. It's just performed in an object comparison instead of an index comparison. So, removing the operation. If the element's found, take it out. And we've actually looked at linked list already, and the two components of the linked list is the data that the linked node is actually containing in this next item. So we have previous and current in terms of a doubly linked list, where we can go to the left or to the right. Each item in this linked structure is only familiar with their neighbor. They're not familiar with the rest of the items. So we have to go node to node, hopping in some way, left or right, and comparing the next item, and the next item, and the next item, or the previous item and the previous item, until we get to the item that we're interested in looking at. And here's the doubly. Actually, this was a singly. It's only going next, next. If we add a previous to it, then we have a doubly. So the only really difference between a singly implemented linked list and a doubly implemented linked list, are we keeping track, is each node keeping track of just one neighbor, or is it keeping track of two neighbors? If it's keeping track of two neighbors, it's a doubly linked list. So doubly linked list has references in each node. One is the next element of the list, and the other one is the previous element. A lot of people don't realize it, but they put together doublies because they want to make sure that they don't lose items in the list. And then you can really mess up a doubly if you don't set the previous correctly. That's the biggest problem with a doubly linked list. When there's only goes in one direction, and it's usually the next, the next, the next, like the singly. You have two nodes. This guy knows about his neighbor, and you want to insert a node. So you make this guy know about this guy, and then this guy know about this guy. And you kind of do like a V in terms of and this guy kind of comes up in the middle, and now he's part of the list. What people forget is, although this guy knows about this guy now, and this guy knows about this, they forget the other part. Now this guy's got to know about this guy, and this guy's got to know about this guy. Because if you don't set the previous side of it, when you go through to go to the previous, you go ding, 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 the list stopped. We skipped an item, because we didn't reset the previous, we only set the next. So it's twice as much work, long story short, when you do an insert, twice as much work when you do a removal. Which makes the doubly linked list not as efficient, going back to the algorithm efficiency concept. You got more work to perform. So if you don't need a doubly, don't use a doubly. Only use a singly linked list, because there's fewer lines of code, a lot less links to actually consider, fewer pointers to work with, simpler concept. Can't talk today. And it basically gives us smoother implementation. But there's cases in which you need a doubly. If you've got to traverse the list in both directions, which makes it more efficient. Here's the catch to it. It makes it more efficient for algorithms. If you can go both ways, you don't have to go all the way to the end, and then go all the way to the front, and then go all the way to the end again, and then go all the way to the front. To search, you can stop halfway and go the other direction. So depends on what you're doing in terms of the algorithms that are searching and manipulating the data in the link. The extra time taken to keep track of the previous ones might pay off in terms of the searching efficiency and the extra capabilities that you might have in terms of the implementation. So it makes moving back and forth in the list easier. It eliminates the need for a previous reference in the particular algorithm. So if you only have the next, you got to take the next and copy it to previous. Take the next, copy it to previous. Take the next, copy it to previous. Instead, if you have the next and previous, you don't have to copy anything, is what that's saying. You already have all that information available to you in each one of the nodes. So when traversing a list, you don't have to keep track of the back, where you've been, the history. You already know the history. There is, however, a bit more overhead, again, with managing a list, and I've kind of described the overhead to you already, I believe. There's the doubly node class. Only difference is we've got a next, a element, and a previous. Usually I put the element up front and I go the next and the previous down below. For ordering, it kind of makes it a little bit easier to remember that it's a doubly. So you put the next and the previous together. But it doesn't really matter what order you actually implement the data members in. Knowing that each node is inside of each doubly node linked list. So we have the list and we have the nodes. And the list is keeping track of the functions that are associated with each one of the nodes. And this actually makes sense in terms of, a lot of people would implement, this is done separately. A lot of people would implement, in fact it is implemented inside. A lot of people would implement the nodes inside of the list. You can actually do it separately. This is nested. You can actually do it without nesting them. Create a bunch of nodes separate outside of the list, and then create the list object. and then add the nodes to the list. This is done by creating the list and then creating the nodes inside of the list object. So you can have them both nested, which is the more efficient way of doing it, actually. Easier way of organizing it. But how you create it doesn't really matter. So, functionality is still there. It depends on the abstraction, what makes it looks easier for you to manipulate. Creating a node, so let me see, go back to center here. Beginning here, we're doing this a manual way. We are creating a double node of an element E, and then we're just going to store elements because we created a class element that was called an E. And we have an element that's a previous, we have an element that's a next, and we're creating an empty node here by making it all null. Then we're going to create node and store a specific item in here. So the node is going to store an element. The element's going to come in and it's going to be added to the element. And we still have null set for the previous because we don't have any other items in. So when we put our new item in, our next item in, so to get the next, it's going to return next. Next is null, which means there's only one item in the list. So we could set that to end. We could set it to start. We could make up variable names and things. Rather than setting it to null. But it's more common to see it set to null just as a placeholder because you can check for null. You can also check for it first or last as well. Returns the node that precedes this one, the previous, return the next. Let's see, set the node that follows this one. Next is equal to D node, which is going to be the previous node. Or, no, next, yeah, it's going to be the new node that gets loaded in. So. Essentially what you're doing is just setting the neighbors, so each node is aware of the previous node and on the future node. So whether you're starting it at the top of the list or the back of the list, you're going to set one of them to null to say, I'm the last one, or I'm the first one. So, and I'll skip through the code here because you can actually download the code, take a look at it. Actually, if you have the textbook, you can download it from the author's website. Actually, even if you don't have the textbook, you can download it from the author's website. There's the Doubly linked list, where you have the front of the list and the rear of the list. They should have a copy of the book actually in the library here, the ITU library. You're supposed to have a copy of it. I have a copy of it too if anyone wants to borrow it. But now with the internet these days, it's easier just to get it off the internet. So, otherwise, if you get it from a book, you got to copy it in yourself. Maybe you can just download the stuff and do it. But you don't even need that. I got other examples as well. So, anyway, here's a picture of it. It's going in both directions, forward and back. Lo and behold, it's just like I described. It's a picture of a doubly linked list. So let's revisit the remove method for the linked implementation of the list. This time using the doubly linked list. When we remove it, notice how much more elegant the code is in this version compared to the earlier version. It's actually, it's easier because you can go forward and back on it. It's not as, it's a little bit more explicit. So the cost of the elegance is the overhead associated with storing and managing the additional links. So I prefer actually the singly, and I think the singly is more elegant because it's fewer lines of code. But this one is more explicit, because you have 2 instead of 1 variable to specify. But I guess this might be clear to a lot of people. So you can set the previous and you can set the next in any order you want as long as you set them both. So removing an item, you can find the item a little bit easier. You find the node that you want to remove. You get the node elements. You check to see if it's at the front or the rear, which is kind of interesting because those are special cases on a linked list. In an array list, we don't care where it is in the list. It doesn't matter. We have to do the same operation regardless. In a linked list, we care whether it's at the front or the tail. We get it. We find the previous, we find the next, we reset the previous, and we reset the next, essentially. So in both the arrays, in the array and the link implementations, they may vary. Many operations are similar in efficiency, actually, between the two. They both have pros and cons. Most are big O to the one, except when shifting and searching need to occur, and then you're looking at, depends upon how much searching and sorting actually needs to be done. In this case, you can increase it by the order of how many times you have to rewrite that list. It's going to raise the big O notation. So Long story short, it's the adjustments that you have to make that add to the efficiency, that reduce the efficiency of the algorithm implementation. So in particular, situations, the frequency of the need for a particular operation may guide the use of one approach over another. In cases in which you're going to load data up and you're never going to add and remove, leave it as an array list. In cases in which you're going to add and remove constantly, create a linked list structure where you don't have to print it out all the time, but you're just going to add and remove a lot. So you could theoretically take and implement a list of items and switch it back and forth, but that would even be more complicated. Better, if you're going to use a data structure to hold a list, use the same data structure for the entire life of the program. Because if you take and you say, well, let's create an array out of this, because I've seen students do this, actually. It's not in data structures courses, it's usually in programming courses. They take the array and they copy to another array, and then they copy that array to another array, and they copy that to a linked list structure. You know, whoa! That's a lot of sorting through the list, copying all the items, putting it into another list. You're just switching the list around because you need it for a different purpose. So the concept being is you're supposed to take one data structure, use it for the life of the program, but find the right data structure that's going to meet the needs of what it is you need to do. So let's do it and say, resort the array and just rewrite the array out, because then I don't have to sort it again. Which makes sense, actually. But why are you using an array if you wanted to sort it order like that? Anyway, here's some examples, some Java list implementations. These are actually out on the bhacker.com website. If you click on it, I think we're going to get an error message, but let me just see. Nope, it's going to go take us to the Oracle. Well, actually, I believe I was at the end of the slide set. Yeah, actually, no, it should take us to the, it's taking us to, well, these lists, okay, these are the built-in Java. I was like, what is this taking me to? It's going to take me to the built-in class vector that's going to show me all of the, if I wanted to make a vector as in this example, because I clicked on the vector link. For this particular, if I want to extend abstract list, and I'm going to implement list and all these other clonable and comparable and serializable, all the other interfaces that might be associated with this functionality that I want to implement, it gives me all the documentation for it. I personally don't like the Java docs that are out here because it reads like Greek, but some students prefer it. So at the end of this lecture, these links do work actually, and they go to the, if you want to read the Java doc stuff and the Java information, it will work. So looks like we're going to get out early today because well, most of the stuff we covered already, which is interesting. But Chapter 6 was kind of a review, I think, in a lot of cases. So next week I'm going to try and bring in some more source code examples because I like that, but I usually go like every other week or so in source code examples. And talk about, I've already gone through the assignments for the course, so talk about a few more advanced things that we can do with links, with lists. What I'd like to do is bring in a couple of different problems, you know, like some scenarios, like some games or something, and say, this is how I would create the linked list for it, or this is how I create an array list, and kind of compare the different implementations. So that will be next week. All right, thank you for coming, and I will see you next week. We're getting a little loud in the back, but it's good. You can talk as much as you want now. We're all done. Sign the roster, and you're done. And as soon as it starts getting loud, we're done.